All right, so for our lecture today, I'm going to start by revisiting this idea of degenerate orbitals and show you a different representation of the orbital in a way that we can still think of these as degenerate orbitals, meaning that when we put electrons into these degenerate orbitals, they're still specifying the same energy level, in this case a sublevel, but they're only occupying one section of that available energy level, and they can't overlap with the other sections. If we're talking about, just to remind you, this is the orbital, and for the orbital, it's the square of the waveform, right? Psi is the waveform that we get from solutions of the Schrodinger equation. And when you do the square of that, you get that theoretical probability distribution of where electrons can be found at any given time, given that we can actually never see where they are at any moment in time. Okay, so for a sphere, all right, for S, there's only one orbital at the S sublevel. So it's easy to imagine that as a sphere. There's only one orbital, there's two electrons in any orbital, and so where probabilistically can those electrons be found? It's somewhere in that sphere. Now that's true whether we're at the 1s level, the 2s level, or the 3s level, okay? But as we increase in principal energy level, we are increasing the distance that those electrons can be found from the nucleus. So that's what you're seeing here with these spheres. There's a little nucleus, and remember from the Rutherford model, right? The nucleus has most of the mass, but almost none of the volume. So there's a nucleus in there, but as we increase in N being the principal energy level, the distance is further from the nucleus. Now, we also know from part of our earlier discussion that if we actually were to look inside this sphere, you wouldn't just get a random distribution of those two electrons within that S sphere, right? That has to do with this radial distribution pattern that I kind of showed you here. Here's just 1/4 of a slice of that sphere, all right? The electron probability, it's not just equally diffused through that sphere. There's certain areas where you've got an increased probability, and then there's a node of low probability, and then another area of increased probability. And the higher the N is, the more of those nodes you have, the more of those kind of stripes of probability you have within that sphere. So it's real complicated, okay? I'm trying to keep it simple for you, but show you that it's not as simple as we might just describe. But if we're just looking at the overall shape of what an orbital at the S sublevel would look like, we can imagine that as a sphere of probability. It gets a little more complicated when we start getting to the P sublevel and the D sublevel, because there we have the degenerate orbitals. So it gets a little more complicated when we get to the degenerates. Now I use the simplistic example of imagining this lecture hall as one sublevel, and we divide it into 3 parts, okay? But that doesn't quite make sense with the overall idea of, well, how can it be the same energy level of a third of you are over here and a third of you are over there? So when you actually plot out the square of the waveforms, the square of psi, at the P sublevel, you end up getting, instead of a spherical distribution, you get these bilobed distributions that I have over here in blue, okay? So these are bilobed. Sometimes they're called dumbbells, dumbbell shapes. And it's a little deceiving because when you look at them, you say, oh, well, there's 2. Like if I just look at this one over here, oh, well, there's 2 lobes. So there's 2 orbitals there. No, that's one theoretical distribution for one of the orbitals. This is one orbital, and we're arbitrarily labeling that in the X orientation. And then the second one is then set for the Y, so 90 degrees offset from that. And then the Z in 3 dimensions. Those are just arbitrary X, Y, Z, because overall we have these 3 degenerate orbitals. Each one of them has this bilobe distribution, okay? And so they are going to be offset by each other by these 90-degree orthogonal directions. If I were to just highlight one of them, here's one in blue, okay? So this is one theoretical distribution for one of those p sublevel orbitals. In red, I'll show, here's one that's in the y plane, all right? It's going along the y-axis here. So this is called 2p sub y. But again, the y, the x, that's just arbitrary. But if you set one as being the x, then the y will be 90 degrees offset from that, and the z, and so on and so forth. All right, the third one, it's the same overall shape, it's just oriented in a different direction in three-dimensional space. So if I were to put two electrons into one of these orbitals, let's just go back to the one in the x direction. Now don't write this down because I'm going to move them around, okay? But we know that there's two electrons in each orbital. So if I had two electrons in the p sub x orbital, I can put both of them over here, or I can put one on one side and one on the other, or I can put them both on the left-hand side or the right-hand side. It doesn't matter. It's one distribution. It just looks funny because it's in two bilobes, and there's a node at the center. There's no probability. Zero probability at the very center here. What's at the very center? The nucleus, okay? The same is going to be true for the spherical representation of 1s orbital. If I go back to those radial distribution patterns, I think I pointed this out to you. There's another node here, maybe I didn't point it out, right here at the center, there's the nucleus. If we had a more detailed diagram, you'd see that there's no probability of an electron being found at the very, very center there, because that's where the nucleus is. So there's a node there as well. Okay, so we have these nodes for the p sublevel orbitals, but how does this still define three non-overlapping exclusive regions that all specify the same energy level? So I'm going to try to show you that now by overlaying these three colored outlines of each orbital, and I'm going to put them all over the the one on the right. So the 2p sub z, that's in green. I'm going to overlay now the one that was in blue. Actually, let's do the one in red because that one's coming out this way. So this one's in the y orientation, right? And then I'll take the one that was in the x in blue. That one started, it's kind of behind here, and then it's up in front here. Okay? So I've taken those three bilobes and just overlaid them. And hopefully in doing that, you can see that that is now starting to take the overall shape of a sphere again. If I were to exaggerate how those bilobes are actually drawn, you would see that when you overlay them all, now we have the sphere, which defines that sublevel, the p sublevel. But within that p sublevel, we have these three different bilobes that are oriented in such a way that any two electrons are in one of them, but they can't overlap in the probability space of any of the other two. Okay? So it's really not dividing this lecture hall into three equal parts. It's more like this. And this is actually using the theoretical distribution of where those p sublevel electrons could be found in any time. It gets even more complicated when we get to the d sublevel, and even more complicated when we get to the f sublevel. So I'm just going to show you the pictures, but it's really the same idea. Now at the d sublevel, so these are the d sublevel, we have 5 degenerate orbitals. But they're all degenerate, so they all specify the same energy level, sub energy level. So these we call clover leaves. And we don't need to worry so much about how they're designated, like sub xy, sub xz, sub xy, x squared minus y squared. Don't worry about that, okay? I just want you to get the overall idea. It's way too complicated for me to try to overlay all 5 of these into one, just like I did for the p's. But you can kind of imagine that if I did that, we are once again going to end up describing an overall spherical shape that defines the d sublevel within any given principal energy level. All right, it's the same idea. All right, so here for all of these, we've got 2 electrons in each orbital. let's go ahead and fill these in here. I'll do it with the P's, because how many electrons total can we get in the P sublevel with 3 orbitals? There's 6 electrons that we can fit in here, because there's 3 orbitals, and each orbital can hold on to 2. So we've got 3 sublevels. And if we follow Hund's rule, let's just start filling these in. The first electron can go into any one of these 3. Remember, they're arbitrary, right? So I'm just going to arbitrarily put the first one in the blue. Okay. The second one is going to go, actually here, why don't I do it on my overlaid one here? Let's do it that way. Although it's going to get a little complicated here. Let's see. Let's put the first one in the blue one. Okay. The second one is going to go into one of the other 2 that are empty. That's following Hund's rule. It's overall more energetically favorable to put these negative electrons into separate regions than to squeeze both of them, force both of them to only occupy 1/3 of the space. So the second one's going to go in either the green or the red. It doesn't matter. Here, I'll put it over here in the red. The third one's going to go in the green. The fourth one, oh, and by the way, all of these spins, they're all going to be the same, right? Because it's slightly more energetically favorable to have all the magnetic spins aligned in the same direction. Whether they be spin up or spin down, they'll all be the same direction. Now, the fourth one has to be double filled into one of these. So let's just put it in the green one. But once again, if I put it in the green one, it could be up here. And that's just the same as me putting it down here. That green bilobe distribution is 1 orbital. Right, so I'll just put it up here for simplicity. And then that's 4, 5, and then 6. Okay, so just again, emphasizing Hund's rule, but showing you how these can now all occupy the same energy level, but be restricted to 1/3 of the space. And the same would be true if I did this with the d orbitals. It's just more complicated. But how many electrons total can we fit in the d sublevel? 10, because there's 5 orbitals, right? 2 in each orbital times 5. So we have room for up to 10 electrons. Here, times 2 electrons, we have room for 6 electrons total. And at the s sublevel, there's only room for 2. Okay, so that gives you another way to think about degenerate orbitals here. All right, now I'm going to talk next about a couple of oddities, more oddities that you find when you try to apply these rules to electron structure within an atom. Last time we talked about one oddity, which was that the 4s electrons fill before the 3d electrons. We had that nice discussion, right? 4s fills before 3d. And the explanation for that, one explanation for that I showed you, was going back to these radial distribution patterns and showing you how when you overlay them, there is some small probability where the 4s electrons actually get closer to the nucleus than the 3d electrons do. And when you have a negative charge get closer to the positive charges, they're more stabilized, so it doesn't take as much energy to keep things stable. That's always what we're talking about with the ground state. We're describing the ground state of electron configuration here. It's where we place those electrons in the energy levels in a way that requires the least amount of energy to keep things stable. Now I'm going to copy this distribution over because this also explains the next oddity that we see here. So you can't do this easily, I know. So take yourselves a moment to retrace that, or you can just write these on the sides of the notes where I had this written before. So these are the 4s electrons, and in red we have the 3d electrons. All right, so we remember the explanation why 4s fills first. But now let's go across our periodic table and take a look. So if we were to write in the electron configuration for potassium, we know potassium is going to have the core of the argon atom, and then the valence electrons would be 4s1. If we did calcium, it would be 4s2. And as we keep going and start getting into the transition metals now, we now start placing electrons into the 3D sublevel. So if we have 3D1, we have scandium. If we have 3D2, we have titanium. If we have 3D3, we have vanadium, and so on and so forth. Now, there are some other oddities that you get into, even in that filling pattern, and I'm not going to discuss those. There's many oddities here to discuss. I just want to show you one or two of them, okay? When we get up to iron, all right, we're going to have this configuration. Now, here I'm just showing you the orbital diagrams. And now I'm showing you the 3D orbitals first and the 4s orbital second. There is no convention for this. Sometimes you'll see 4s written first. Sometimes you'll see 3D written first. You just have to get used to it. You have to get used to seeing it both ways. You should still be able to interpret what you need to interpret, seeing it either way. Okay, so iron is element number 26. So when we fill in, right, we've got the 4s fills in first. So that would be spin up, spin down. And then we've got 1, 2, 3, 4, 5. It's the 6 boxed in. So we're going to have 6 electrons in the d orbital, in the d sublevel orbitals. So let me fill those in using Hund's rule. We'll have 1, 2, 3, 4, 5. And then the 6th one gets double filled in one of them. Okay? And that's the filling pattern. And we understand why 4s fills first. But now the next oddity happens when we form ions. So we've been talking a lot about ion formation. And the metals, are the metals going to gain electrons or lose electrons to become more stable? They're going to lose. And when metals lose electrons, they form positively charged cations. And that's what we're doing here with iron. Now, in this case, iron's not going to lose all 8 of these electrons. That's a lot to lose. But it does lose some of them. It can lose 2 of them, it can lose 3 of them. But I just want to show you what happens when they get lost. When things get ionized, what has to happen for things to get ionized? Where does the electron go? Does it go to a higher energy level? Or does it leave the atom completely? It leaves the atom completely. Now, in the flame tests that you all did in lab this week, you were giving the atoms energy and you were seeing lights, but those lights were from the electrons being excited to a higher energy level and then losing that energy and going down to a lower energy level. Those electrons were not leaving the atom. You weren't forming ions. It takes more energy to get electrons to leave the atom completely and form ions. So ionized, the electron leaves the atom. And that takes some energy. It's called ionization energy. You need to overcome that ionization energy to get the electron to actually be so excited that it leaves the atom completely and never comes back. Right? That's energy needed for the electron to actually escape, or let's not say escape. Let's just say leave the atom and never come back. Now we're going to take a look at ionization energies of different elements today, right? But here's the idea of it. If we're going to form ions, which are the easiest electrons in the valence shell here to leave the atom? Is it the 4s electrons or is it the 3d electrons? What do you think? You can kind of tell by looking at the orbital diagram. The 4s leaves first. Look at their distribution. Most of the time, the 4s electrons are further from the positive charge of the nucleus. Which means that it takes less energy to get them to ionize, to get them to leave. The 3d electrons, even though they fill in last, it's curious. They fill in last because they specify a higher energy level, and we showed that by the fact that they don't get as close to the nucleus in general than the 4s, because there's some small probability that the 4s gets closer. But most of the time, the 4s electrons are very far away. So if it's forming an ion, they're the first to leave. All right, so it seems a little backwards, forwards, but it's not really. We're not talking about exactly the same thing. One is talking about the energy level as we fill them in. The other is talking about how much energy does it take to get them to leave. Okay, so the 4s electrons, they ionize before the 3d electrons. And the same would be true if we were at a higher principal energy level. If we were at n equals 5, then we'd be having the same discussion about the 5s and the 4d electrons, or the 6s and the 5d electrons. Okay, so it's curious. All right, 4s fills before 3d, but 4s electrons are easiest to ionize, are easiest to remove. So they'll have a lower ionization energy. Okay, and you can see this trend very easily with all the transition metals. Because when we're working with transition metals, we have the s electrons, the s orbitals are filled with electrons before the d sublevel orbitals are filled. So when these form ions, they're going to lose these first. And again, the same would be true if we were down here or down here, relative to the d orbitals that are being filled right after them. Okay? So there's more curiosities than we have time to discuss. If you're interested in any of them, and there's time, we can always chat about them in office hours. The textbook goes into a few of them, but I just want you to stay focused on this particular one, because you'll see this a lot. All right, here's some other things that you see, other trends that we can describe with the periodic table. So let's look at some other periodic trends that you tend to discuss with this subject. So ionization energy, all right? I told you we can look at the trend of ionization energy in different elements. There is a general trend. You'll find that ionization energy here, let's call that IE for short, all right? Ionization energy increase as you go from left to right across a period. So for example, a period 2, if we go to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, as we get closer to fluorine, it takes more energy to get those electrons to ionize. Okay? There's only one electron in lithium, right? One valence electron. You know how to find that out now, because what's this number at the top? 7. There's 7 valence electrons in fluorine. It takes more energy to get any one of those 7 to ionize from the fluorine atom than it does to get that one to ionize from the lithium atom. Now you can think about this in a qualitative way. We already discussed that elements are going to either gain or lose electrons to be isoelectronic with their nearest noble gas. So lithium and beryllium, their tendency is going to want to lose electrons to be isoelectronic with helium. So if you're going to lose electrons, it should make sense that it doesn't take much energy to get those electrons to leave. Right? It does take some energy, even though it wants to lose them if it can, it still takes energy for it to do so. But fluorine, oxygen, they don't want to lose electrons. They want to gain electrons. So it's going to take a lot more energy to get them to give any of them up, because it doesn't want to give any of them up. It wants to get them. Okay? So that's one way to qualitatively think about this trend, that as you go from left to right across a period, the ionization energy increases. Now I'm going to show you a little bit different way to think about that in just a minute. But right now, I just want to describe the trends to you. Also with ionization energy, the trend is that when you go down a column or down a family, the ionization energy is going to decrease. It takes less energy to remove valence electrons if you're going down a particular row. And you can make sense of that easily because as you increase the principal energy level, those valence electrons are getting farther and farther away from the positive charge of the nucleus. So they're not as attractive. So it's easier to remove them. All right? Easier to remove. Because they're further away from the positively charged nucleus. There's another trend that you tend to learn about at this stage of general chemistry that we'll talk about today as well, and that's the overall size of the atom, what we call the atomic radius or size. So I'm going to put that over here in green, okay? The atomic radius or size. And you can think of that as, you know, we typically draw these atoms as spheres, right? And those spheres represent where the electron clouds extend to, okay? So think about that as the radius or the overall size. But here the trend is a little bit different. As you go across a period, the atomic radius decreases. As we go from left to right across a period, and as we're going down a row, as we go down a column, right, the size, what do you think? Does it increase or decrease? It increases. I already told you that, right? Because as you increase the principal energy level, those electrons are farther and farther away from the nucleus. So the size increases as you go down a column. Now, those are just the trends, okay? But I'm going to show you something that helps you understand why those trends exist. And it has to do with something that we call effective nuclear charge, which is what we're going to talk about last in this chapter. Here's the slide from your slide pack that talks a little bit more detail about ionization energy. It gives you a more formal definition of it. I already told you it's the energy needed for an electron to leave an atom, so we already discussed that. But it's measured in kilojoules per mole of electrons that are lost. All right, so we're working with moles again. And joules, this is the units of energy that we'll be using later. Kilojoules per mole of energy that it takes to remove 1 mole of electrons from an atom. And you can see the same trend that I showed you here with these rising bars. So the higher the bar is, the higher the ionization energy is. So this is just showing you that, again, it increases as you move across a period, and it decreases, here, showing you right here, decreases as you're going down a column. This is specifically talking about the energy required to remove the first electron. It's what we call the first ionization energy. But we're not going to go into more detail on first versus removing a second one and removing a third one. There's more interesting things to talk about there. But I just want to keep you focused on the trend of how much energy it takes to get 1 electron to leave the atom when it's ionizing and what that trend is. It's increasing. On the right is a related trend that I haven't talked about yet. That's called electron affinity. So here, IE for ionization energy and EA for electron affinity. It's just the reverse. Affinity is how much you love something, okay? So electron affinity, the higher the electron affinity is, the more that atom wants to get electrons. Just like we talked about, oxygen and fluorine, they want to get electrons, because in doing so, they can become isoelectronic with their nearest noble gas and overall be more stable, okay? That's also measured in kilojoules. It's the energy that's released when a mole of electrons is acquired by the atoms. The trend here is the same as the trend in ionization energy. If we say that ionization energy increases across a period, so does the electron affinity. It increases and it decreases. And you can see that in the numbers. But you can also think about that empirically, right? If fluorine has really, really high ionization energies, it's also going to have a really, really high electron affinity. If it has a strong affinity for the electrons, but wants to get more, then it's going to take a whole lot more energy for you to get rid of what it's already got. Okay? So the trends are the same. We're just describing gaining and losing. Where it's opposite has to do with the overall size of the atom. But both of these trends can be very nicely explained by this last subject down here, which is effective nuclear charge. Now, the textbook goes into effective nuclear charge a little bit. I'm going to go into a little bit more detail, and I hope that in doing so, it will explain these trends that we just discussed. You can always memorize what the trends are, but this is why. This is explaining why the trends exist. So I'm just going to take you part of the way through period 2. All right, we're going to go from lithium to neon, and maybe we'll go one beyond to sodium. The idea here is the effective nuclear charge. I've already impressed upon you the attractive force between the electrons and the positive charge of the nucleus. So the closer the electrons are to the nucleus, the more stable things are. You can also think of that as just how much positive charge are the electrons seeing from the nucleus. That's what we call the effective nuclear charge, or Zeff. Right, and up here, it's just reminding you the greater attraction between the positively charged nucleus or protons and the negatively charged electrons, the more stable you are. Now, there's simple calculations and there's more in-depth technical calculations. We're just going to keep it simple. All right. The simple math for calculating what the effective nuclear charge is you just take the number of positive charges that you have in the nucleus, okay, and you subtract from that the number of electrons that are negatively charged that are shielding the valence electrons from the positive charge. It's a shielding. Remember, we're thinking of these as shells, shells within shells within shells. If you have a completed shell principal energy level, that means it's filled with negatively charged electrons. We're talking about the valence electrons. Those are the only ones we really care about. Those are the ones that are being gained and lost and shared in chemical reactions. So we want to be able to track what is the effective positive charge that those valence electrons are seeing from the nucleus. Given that the farther away they are, they're not only far away from the charge, but they're also being shielded from that positive charge by all the negatively charged electrons in completed shells beneath it. Okay? So it'll make more sense when I actually give you some examples here. So let's just start on the left-hand side of period 2 with lithium. Lithium has an atomic number of 3, so it's got 3 protons. So I'm just going to draw them in here at the nucleus. So there's 3 protons. I should have drawn a nucleus in there. And then we're going to use the Bohr model of increasing energy levels, and I'm just going to place electrons in there. We don't care now about S sublevels and P sublevels and whatnot. I may organize the electrons that way, but now we're just filling electrons into the overall principal energy level. Lithium has 2 electrons full at n equals 1, and that third electron goes into the valence shell n equals 2. If I were to calculate what's the charge, what is the charge from the nucleus that this valence electron is seeing? Okay, so that effective nuclear charge, Zeff, is equal to the number of positive charges from the nucleus, that's 3, minus the number of electrons that are in the completed shells beneath it. That's going to be 2. Think of it as insulation. Even though there's 3 positive charges in the nucleus, that one valence electron is really effectively only seeing a 1+ charge from the nucleus. You see that? Let's take it a little further now. Let's go over to carbon. Carbon has 6 electrons in the nucleus. Again, it's got 2 in the completed shell, so that's your shielding. And now it's got 4 electrons in the valence shell. 2 are in the S sublevel and 2 are in the P sublevel. But for this, it doesn't matter, okay? Now let's describe what the effective nuclear charge is for any one of those valence electrons. How many valence electrons are there in carbon? It's only 4. There's 6 total electrons, but there's only 4 valence electrons. The effective nuclear charge that I would calculate should be the same for this discussion for any of those 4. I can circle any of these 4 to do this discussion on. Let's just circle one of them. The effective nuclear charge on that one is going to be the number of positive charges in the nucleus, that's 6, minus the shielding, 2. That's going to be equal to 4 positive. Okay? So any one of those 4 electrons are seeing an effective nuclear charge of 4+, whereas in lithium, it's seeing an effective nuclear charge of only 1+. So they are more attracted to the nucleus. They're seeing a stronger positive charge from the nucleus. So that's going to bring them in closer. The atomic radius shrinks. And I tried to show that to you here on the slide. As we're going from left to right, the circles are getting smaller. They're shrinking because there's more of an attractive force on any of those valence electrons in carbon versus the 1 valence electron in lithium. You see that? Right? The trend continues. Let's go over to fluorine. Fluorine has 9 protons, so there's 9 positive charges in the nucleus. And the electrons, we've got 1, 2, and then 3, 4, 5, 6, 7, 8, 9 electrons. But only 7 are in the valence shell. So if we pick on any one of them, doesn't matter which one, the effective nuclear charge here is going to be 9, which is the positive charges in the nucleus. The shielding is still 2. So now these have an effective nuclear charge of 7+. So they are really being drawn in. Okay? You've got a stronger attraction of any of those valence electrons to the higher positive charge of the nucleus. That explains why the atomic radius shrinks. That also explains why the ionization energy gets higher and higher, because any one of those 7 valence electrons in fluorine is much more strongly attracted to the positive charge in the nucleus than the valence electrons are in carbon or in lithium. It's going to take more energy to overcome that stronger attraction. So the ionization energy increases and the atomic radius shrinks. Right? This explains it. Now let's take it all the way to neon. So neon, we're going to have 10 protons, and now we've got 1, 2, and then 3, 4, 5, 6, 7, 8, 9, 10. I think you all know what the effective nuclear charge would be on any of those valence electrons, right? What's it going to be? Should be 8+. Okay? So the strongest yet, and it's the smallest yet. But now what happens when we get to sodium? With sodium, whoops, and we've already seen this, okay? We've got 1 more electron to place, but now we are out of energy levels at the n=2 principal energy level. We're out of orbitals. We're out of sublevels. So that next electron has to go into n=3. So let's plot that out. Here we have 11 positive charges in the nucleus. We still have 1, 2, n=1 is full. n=2 is now full. 1, 2, 3, 4, 5, 6, 7, 8. We're full with 8. And now that 11th electron has to go out here at n=3. What do you suppose the effective nuclear charge is of that valence electron in sodium? Let's calculate it. The effective nuclear charge, now we have 11 positive charges in the nucleus. And what's the shielding now? How many electrons are in full valence shells in lower energy levels? There's 10, right? Because everything's full now. That's going to equal 1+. We're back to the same effective nuclear charge that we saw in lithium. But it's also farther from the nucleus. Okay, so that explains why the atomic radius is increasing. We already discussed that. But now for the valence electrons, as far as stability is concerned, right, we're looking at the valence electrons. When we were at fluorine, all right, we had an effective nuclear charge on the valence electrons, that was 7+. When we got to neon, the effective nuclear charge on the valence electrons was 8+, the strongest yet. When we now go to sodium, the valence electron effective nuclear charge is back to 1. So if sodium can give up that electron, if it loses it, it goes back now to being isoelectronic to neon, where the effective nuclear charge on the valence electrons is much higher again. You see that? It's pretty cool. So it also explains why the noble gas configuration is the most stablest, right? We've been saying that as a rule. That's what their driving force is. They want to gain or lose electrons to become isoelectronic with the nearest noble gas, because that's the most stable. Now you can see why that is. All right, so this also explains why it is that the noble gas configuration is so stable. This little grid here is just showing you the atomic size. Because I didn't show you that earlier. That's just from another textbook. It just shows you the general trend. It's not absolute. There's going to be little fluctuations in these trends, but the general trends are as I've been describing them. All right. Noble gas configuration is most stable because it has the greatest effective nuclear charge on the valence electrons. Remember, it's all about the valence electrons, not just all of the electrons. All right, let me take it one more step. Let's go back to iron now. Remember that oddity with iron that I showed you as any transition metal? It's the 4s electrons that will get lost first when forming ions. So let's take a look at that now with the exact same idea with effective nuclear charge. So let's draw them all in. We've got 26 protons in iron, which means we need to put 26 electrons in here. So 2 go at n equals 1. 8 go at n equals 2. 2, 4, 6, 1, 2, 3, 4, 5, 6, 7, 8, 1 too many. Okay, now we're full with 10. And then we fill in the 3s and then the 3p. 1, 2, 3, 4, 5, 6. Again, they're all the same here. They're all within the shell. I'm just sequestering them so I can keep track of my electrons. Okay, because after 3p is filled up, then we fill in 4s first. And then we go back and fill in the 3ds. So, and there's 6 in the 3ds. Let's put them in here. 1, 2, 3, 4, 5, 6. Okay, so let's just notate these are the 3ds that we're talking about, and these are the 4s's. Now let's take a look at what their effective nuclear charges are. If I pick on any of these 2 4s electrons, the effective nuclear charge is going to be the number of positive charges in the nucleus, so that's 26, minus what's the shielding now? What's the shielding? Well, it's more than 10. We've got 2 here. We've got another 8 here, so that's your 10. But then we also have another 8 here. Okay, that's 18. Plus we've got those 6 electrons from the 3D as well. So 18, 19, 20, 21, 20. There should be 20, what is it, 24? There's 24 electrons in the shells beneath 4s. So the shielding here is 24. So the effective nuclear charge on any of those 2 4s electrons is going to be 2+. Okay. What's the effective nuclear charge on any of these 3D electrons? Well, still have 26 positive charges in the nucleus, but now what's the shielding? What is it? Let's take a look. We've got 2 at n equals 1. We have another 8 at n equals 2. And now we're looking at an electron that's in n equals 3. So the shielding is only 10. Okay. So the effective nuclear charge on any of those 3Ds is now going to be 16 plus. Okay. So there's a much stronger attraction to the nucleus on any of those 3D electrons than there is for 4s electrons. So this also gives you another explanation for why the 4s electrons are lost before the 3D electrons are when you're forming ions from transition metals. Even though when we're filling them in, following the Aufbau principle, we fill in 4s first because of this, right? Because some probability, they do get closer to the nucleus. So it's still a proximity argument. So you can think of it both ways. It's further away, or you can think of it, there's another explanation just looking at effective nuclear charge. The effective nuclear charge actually explains a great many of the observations that we talk about in general chemistry that you typically just learn about as rules. So hopefully this gives you more insight into why those rules exist, why the atomic size decreases, why the ionization energy increases, and all that jazz. All right, so that's the content for this section